Hello class, and welcome to today's lesson on the dot product. Now you might be saying, what is the dot product and what's the point of it? Well, let's just start off by saying we have two different vectors. One's v and the other one is u, and I'll do this in blue. So these two different vectors, one is defined as x1, y1, and I'm going to need some space. Let's just move this one over. Okay, and this one's going to be defined as x2, y2. Now, just with that given information of these points, just any general x and y, well, we don't know what is the angle between them. We don't know if they're perpendicular, we don't know if they're parallel. So actually there's a method here called the dot product that we use to determine if they are perpendicular or parallel. So we take vector v and vector u, and we put them in the dot product by signifying it with this dot. Now you may have gotten this confused with, or you may have seen it as multiplication in the past, but for here on in we're going to be using a dot to signify only the dot product, which equals x1, so you take your x terms and multiply those together, plus your y terms that are also multiplied together. It doesn't matter which one you write first or second, but this is the way you would write the dot product. Overall, we get an output here, and this output signifies something too. We get some output, I'll put this as a question mark, or actually underline it, that this area here can be giving us a lot of information, telling us if, in some cases, if it's parallel, these vectors, or if they're perpendicular. So the dot product does get and yield a value here, but what does this value signify? It's going to give us some relation that there is an angle between vectors v and vector u. So let's talk about some key examples. One of our key ones is if they are perpendicular. We actually get a yield here that states, and I'll point to this, a yield here that states that the dot product of these vectors must be equal to 0. So that's note 1. Note 2 is if they're parallel, is actually something very simple to say. They're parallel if, and this is sort of related to the dot product, a little bit less, to say that if you have this vector here, and it's equal to a scaled amount, let's call this in blue, k, to the other vector, they are considered parallel. And you can see this in just a moment when we draw some vectors out. So let's get started. I'm given a question here on the right that says given AB, the vector AB, is equal to 3, negative 4, find a vector that is first parallel and then perpendicular. Now I will state that these answers can vary and you can have different ones, and that's totally fine. The first thing I'm going to state is that with that parallel, we're just going to look for some scaled value. So if I have vector AB equaling 3, negative 4, well, let's say I had another vector, we'll call it CD. CD is just going to be some scaled factor. So let's call it just 2. 3, negative 4. Well, I'm going to get 6, negative 8. And that is a perfectly legitimate answer. This is my vector. The answer would be CD, vector CD is equal to 6, negative 8. And there we go. That's a parallel vector. Now remember, for perpendicular vectors, now for part B, we're looking for AB, oh, that's a terrible B, dot product of, let's do EF, because why not? EF here is going to give you an answer that's equal to 0. Let's plug in what we got so far, which is 3, that's going to be multiplied by the second F, so X here, or second X I should say, plus, this is going to be multiplied negative 4 times the second Y. So together, these values have to sum up to being equal to 0. Now I know your first point must be thinking, oh gosh, one equation, two variables. the best way to say it is, remember, your vector is going to be in terms of x and y. So you're looking to create a zero value. Now, this could be many different ones. What I'm actually going to say is this one, I would simply just write it as 3x is now equal to 4y because I added 4y to the other side. And if you divide each other from each side, you can get 3 divided by 4 is equal to y divided by x. Well, this is, again, let's focus on this, your change in the y and the change in the x. And that's actually, we can use that as our vector here to say that vector EF is simply equal to 4, 3. Box that off. And I will state, you can actually see this really nicely, and I'm going to draw it really quick, is this idea, if we draw the first vector AB, that's going to be 3, negative 4. That's going to be approximately down in this region, right? Draw it from the origin. That was a terrible arrow. But the idea is if I do my next one, 4, 3, well, 4 is going to be along this x-axis a little farther out, right? And then go up 3, you're going to get something like that. I don't know, as such, but you can actually see this is most likely going to be, if I drew it correctly, a perpendicular vector. So this does work out, and that's how the dot product is useful. So make sure you get used to, if you see dot product, okay, let me highlight it here now, you do this, and I'm going to get rid of the eraser, the equal signs, no point to having that there, and there you go. Alright, let's consider now the angles that are in between perpendicular and parallel. So I hate to say memorize here, but unfortunately that is true. We can memorize this next part because it's a little bit convoluted. You can try it on your own if you'd like, if you would like to figure out how the proof of this is done. But the angle between two vectors, as follows, is written as cosine theta. So it's in terms of cosine, with the dot product of u to v over, this is where you have to make sure you write this, the u vector magnitude multiplied by the magnitude of the v vector, where you're looking at theta can be between 0 and 180 degrees. I'm going to box this. This is huge. This is one you definitely need to know. So we're going to just throw this into an example problem. That we have to the nearest degree, find the measure of theta, the angle between the vectors 1, 2, and 3, negative 3, 1. So let's do this workout, and feel free to use the formula above as reference. So you're going to use the dot product, or you're going to say that cosine theta, you're looking for theta, is going to be equal to the dot product of your two vectors. So that's going to be 1 times negative 3 plus 2 times 1 over, and this is where you have to do your distance formula for the vectors. That's going to be 1 squared plus 2 squared for that vector, multiplied by, a lot of parentheses, and this one here is negative 3. Don't forget to put that in parentheses, plus 1 squared. All right, I'm going to take my work up to the right and continue it here. So cosine theta, we're still solving for that, is going to be equal to negative 3 plus 2 over, in this case we're going to do the inside here, which is 4 plus 1, that's going to be root 5, multiplied by, this is going to be, oh I forgot to close that parentheses, this is going to be 9 plus 1, that's going to be root 10. Okay, we still go further, cosine theta, you're going to get negative 1 on the top, with root 50 in the bottom. And if we keep going further, actually, I would say at this point you probably could have plugged in your calculator, but I'm going to say theta is then arc cosine of this negative root 50. So be careful how you plug in your calculator, but once you're done, and you're very careful plugging in your calculator, you get theta to be approximately, it says nearest degree, so whole number, you're going to get approximately 98 degrees is your answer for this. So, and this tells you that if you had these vectors already, these vectors, and let's call this vector AB and vector CD in this case, that the angle between them, without putting them in geometric form, we're going to get an angle theta equaling between them 98 degrees. So this is extremely handy, and I tell you to add it to your toolbox. So I hope this was interesting, that I was able to show you through and how to. That's Nala, thank you for that. How to use the dot product and how to find angles between your vectors. See you all next time, and I hope you enjoyed.